the light front, how this embeds causality and frame independence. Not only Lorentz invariance, but even Poincare invariance. We discussed ADS5 and a little bit about the higher Fock states of the proton. This will come back in. Here's a couple references, actually, the work that I'm talking about, light front holographic QCD, and also the meso-baryon tetraquark supersymmetry. So there's two big reviews. So, what we really want to explain is the remarkable features of hadron physics, including color confinement. How is it possible quarks and gluons are permanently confined? Where the mass scale comes from? How the pion can be both a bound state but massless if the quark mass is 0. The QCD coupling at all scales. I showed you a little bit of how that happens. And then what I am going to discuss tomorrow is how to set the renormalization scale to avoid one of the major uncertainties in particle physics, which is how to actually set the renormalization scale and get the answer correctly for any scheme choice. MS bar is just one scheme out of millions. So I'm going to show, in fact, how to get the answer which does not depend on the renormalization scheme, and how it's related to the same procedure we've always known for QED. Poincare invariance, I've mentioned that. There's no Lorentz contraction. Causality, we don't want to violate causality. We don't want to transfer information beyond the speed of light. That's light front dynamics. Everything has to be relativistic. It has to reduce correctly to the non-relativistic forms, of course. Mesons and baryons display supersymmetry. There's exotic phenomena, which I've only barely touched. This will be the first lecture tomorrow, color transparency, intrinsic charm. I told you a little bit about hidden color. Exotic hadrons. I'll mention the octaquark, which is something you've probably never heard of. And also the cosmological constant problem. I want to discuss that. So this amazing thing of light front holography starts out with the observation that QCD really has no explicit mass scale. So where does it come from? So as I mentioned, the alpha Fabini-Furlan principle, they showed that if you add terms linear in the dilatation operator, the special conformal operator, then a mass scale appears magically. But it always gives a unique harmonic oscillator potential, and it also, the action remains scale invariant. That's remarkable. And so when you apply that procedure to the light front Hamiltonian, it tells you there's only one possibility. Now, in reality, we'd love to be able to derive that directly, this kappa 4 zeta squared, directly from the QCD itself. Not possible so far, but that's a goal. But anyway, this fixes the anti-de Sitter space stillaton, e to the plus kappa squared z squared, to show all the spin contributions, spin orbit interactions, and then it looks just like the real world. And then it turns out that if you extend it to superconformal representations, that's Fubini and Rabinovich, then in fact you get actually amazing fact that the meson, baryons, and tetraquarks form fourplets, which are degenerate. And so this is actually some supersymmetric features of the QCD spectrum, which you actually apparently see in nature. So it's actually a very indirect way to understand nature. However, it's getting there. And then this remarkable way of doing the physics is really as simple as Schrödinger theory. The equations are just like Schrödinger theory in non-relativistic atomic physics. And then we have this new radial variable zeta. This variable is actually the radial variable that's, again, frame independent and so on, but it's conjugate to the invariant mass squared. I'll review that in just a moment. So then you end up with a relativistic, frame independent, color confining, unique color confining potential. You get the QCD coupling at all scales, hadron spectroscopy. It looks a lot like the real world. And then wave functions, form factors, hadronic observables. I'm going to show you some of those. Constituent counting rules is built in. And then some new insights into condensates. This was briefly touched on by Craig Roberts last week. And also, I should emphasize this point, that actually there is a way to actually use this method as a first approximation to the real QCD. So this is called basis light front quantization, something James Very and I developed. And the trick is what you do is you use the solutions from this simple ADS model, construct an orthonormal basis, and then you diagonalize the true light front Hamiltonian, the one that comes from the Lagrangian, on that basis. And when you do that diagonalization, then you, in principle, get the right answer. So that's actually one of our goals. And he's been practicing this with positronium right now, in fact. I've written several papers on this. So with this procedure, this anti-de Sitter space model, and with this special radio variable zeta squared, which is, in fact, appears right here, instead of d by d r squared, you get d by d zeta squared. With this variable, with this thing, you actually satisfy the conformal symmetry of the actions because you still have this d alpha Fabini-Furlan procedure. It comes specifically from the anti-de Sitter space with this specific dilaton shape. The light front holography brings you from this mysterious fifth dimension to our world at fixed z, and there's a single variable zeta which controls the physics. There's one parameter kappa that appears throughout QCD, and here I write 0.54 really GeV. However, that's just a human convention because we use electron volts to define things. It doesn't really matter what the parameter is because we're only going to determine ratios anyway. And so here's d alpha Fabini Furlan. The scale can appear in the Hamiltonian, can appear in the equations of motion, but without affecting the conformal variance of the action. And this is something just intuitively what you want to realize, in fact, is that the mass scale really is just simply a placeholder. It's not really determined by QCD. And Fabini and Ravinich, they extended to the supersymmetry. So underlying principles, Poincare invariance, quantization of fixed light front time, causality, this amazing connection between z, the fifth dimension, and zeta, our world, where zeta squared is b perp square x1 minus x. And then you have this fundamental scale, kappa, and a unique dilaton confining potential. And it's the only one that gives a zero mass pion, which is rather startling too, in the zero quark mass limit. And then you get this superconformal algebra, which is the mesons are QQ bar bound states, the baryons are quark, diquark bound states, and the tetraquarks are diquark, antidiquark. And they basically have the same mass, the same Regge trajectories, not just in L, but also in N, the principal quantum number. So this variable zeta, just to remind you, it's x, the light front fraction here, 1 minus x, the light front fraction here, times b perp squared. It's rather mysterious because it's a combination of momentum space and position space, but that's what you get. And it's actually conjugate to k perp squared over x1 minus x, which is the invariant mass of two particles. So that's the joke here. All right. So the supersymmetry, there's a special operator R, which takes you from the antiquark to the diquark. And there's two entries for every baryon, one with L, one with L plus 1. And then the tetraquark, so this is a diquark quark bound state. The quark then can be transferred again with R to an anti-diquark, and then you get the tetraquark. And this closes, the algebra closes within this four-plot of symmetry. And one of the also special things about it to emphasize is that you get equal weight in the proton, for example, between L equals 0 and L equals 1. Unless, and just to emphasize the point, unless you have two different orbiting momentums in the proton or in any nucleon, you do not get an anomalous moment. We don't really think about this very much at all, but the anomalous magnetic moment is actually due to the interference between L equals 0 and L equals 1 in the proton, and so on. So that's important. So this is a review. We started with the light front QCD, the Lagrangian QCD, derived in light cone gauge because it's so simple, the light front Hamiltonian. It has a free term, which is k perp squared plus m squared over x minus x for two particles, and then interaction terms. So at this point, there's really nothing specific to anything I've done. This is just simply what you do just by algebra. You're reducing all the higher Fock states down to this lowest effective Fock state. But then you introduce this variable zeta squared, which is the radial variable. You factor out e to the I Lz phi, and then you have, in fact, this equation. So this equation is that the kappa squared over x minus x is d by d zeta squared. The m squared over x minus x is still there for finite quark masses. There's also a term which is like LL plus 1 over R squared you get from reducing this equation here. And this L is the same L that appears in the phi dependence, but it's LZ, and there's two L plus 1 LZs. And then the potential is totally unknown. However, if you use the anti-de Sitter space, it tells you it's kappa to the 4 zeta squared plus 2 kappa squared. basically J minus 1. And this is, for the case of the pion, the L and S are 0, so you just get the minus 1. So how do you get this formula a little bit? I'll just show you a little bit more. K perp squared over x1 minus x. When you go back to impact space, then you, in fact, and change variables to zeta. Then you find this is the del squared becomes this quantity here. This quantity is the term that goes with the phi. It's L squared over zeta squared. That came up in an hour ago. And then as you go down, you get the 1 minus 4L squared over 4 zeta squared. So I'm just exhibiting the algebra that actually leads you from kappa squared over x1 minus x down to these two terms. Now, actually, people, of course, looked hard at what the QCD potential is. So this is a very interesting paper by Smirnov, and Steinhauser. I thought, always influenced me. And they computed then heavy quark interactions. Here's one heavy quark, here's another heavy quark. One gluon exchange. And then they come to the H diagram, which is, of course, a brilliant thing from the three gluon coupling. And when they compute this diagram, they're startled to see it's infrared divergent. You know, it's actually not finite. Because if you pull the quark and antiquark apart, you get a divergence. It goes off like a log. So this is a new divergence, which is never seen before in abelian theory. And of course, the more of these H's you make, more crossings and everything like that, the more numbers of logs you're going to get. So then you have then a problem that the theory has a new infinity. However, if you say, in fact, that all these interactions sum up to the confining potential, which is something I think is reasonable to assume, that in fact the system self-consistently sums all the H diagrams together into, in fact, a confining potential capital 4 zeta squared for us, then there's no problem because you can't pull the quark and antiquark far apart. So it's sort of like the theory tells you, it hints in perturbation theory, there's a problem here unless you have confinement. But if, in fact, you assume confinement, then there's no problem. So it's self-consistent. Actually, in QED, there is an analog. If you put light-by-light scattering here instead of the gluon exchange, you get a log of ME. Then if you put the mass of the electron to 0, again, you're in trouble. You have a divergence. So you can say, in fact, actually, if you want to make a finite theory with these zero mass electron, you can do it by summing an infinite number of light-by-light graphs. Maybe that's the answer. That actually even QED confines if, in fact, for ME equals 0, which nobody believed before, if you assume all those graphs go together. But that's the logic of this, is that it's a self-consistent solution which solves an infrared divergence. So here, as I say, confinement eliminates the infrared divergences, so it's sort of a self-consistent program. But then once you have the infrared divergences eliminated, you have to have a mass scale to set the range. And that's how, again, how you get the kappa. Okay. So we've talked a lot about anti-de Sitter space. It's a model which actually, from Eldacina, which actually tells you there's this underlying conformal invariance. And then you introduce the stillaton, which gives you confinement, Reggie theory, and so on. And so what you do is you start with this action in the fifth dimension. Now, it comes from a gravity theory, but to me, it doesn't really matter to me. I just simply use it for a tool. And then we just said it's an invariant measure, and it's conformally invariant. And then what we do is we introduce this dilaton profile, which is this extra factor. And this is the magical thing, because it introduces, even in the fifth dimension, color confinement. It introduces a mass scale, kappa. So really what we're doing is we're using anti-de Sitter space as a template for conformal theory and how to break it in a simple way. And then, as we've noticed, this breaking actually leads to a harmonic oscillator, which is exactly what you get from this d-alpha-Fubini-Furlan procedure. So it has a lot of theoretical, intuitive appeal. The question is, does it look anything like the data? And the answer is yes, because it leads to, first of all, Reggie spectrum in both N and L. And that's pretty remarkable. So this is the equation you get in the fifth dimension. We just heard in the previous lecture how you derive this equation, and you specifically get this potential out. The kappa 4 term with a specific term, when you choose the sign right, you get the right term for the spin splitting. And so this is This is the way it works. This goes back to Dash and to Terman and myself. And the equation, as you know, is identical to the light front bound state equation. So this is how you get started, is you say, aha, let's use this as a template, but now we go back to the light front. We identify Z with zeta because the equations are identical. And I mentioned a little bit before, is what got me started in this whole program personally, is I noticed that the Polchinski-Strasser formula for the form factors in ADS5 is the Drell-Yan-West formula when you make this thing. Otherwise, I wouldn't have bothered. And Carlson and company, they showed it's exactly true for gravitational form factors. They're pretty excited too. So this is the way you think. So we have this dictionary which relates the wave function of the fifth dimension to our world. There's one variable zeta when you project out L, and that becomes Z. And then you have, in fact, this thing. Now, this is just the way it works. I can't explain the square root of x1 minus x zeta minus half. But when you make this identification, this is the way you have to do it. You have to pull this factor out and pull this one back here. So I don't have an intuition for that, but that's just algebra. And then there's this identification of UR squared is this thing, but that has to do with twist dimensions. When you look at the short distance behavior that Z goes to 0 in the fifth dimension, you know, in fact, from the operator product expansion, how the answer depends on mu r in the ADS case and these variables in the case of our world. So light front holography, it's a unique mapping which is derived by first of all, the equality between the formulas for electromagnetic and gravitational form factors, matrix elements, and as well as the identical equations of motion. So here we are back again to this light front Schrödinger equation with this beautiful formula. So let me emphasize again, the first two terms are universal. It doesn't matter any tricks you do. That's just algebra. This, of course, is new. All right. Now, when you put this potential in, you solve this equation. You can give it to Mathematica. These are the solutions, and this is the spectrum. And the spectrum is so simple. It's what Reggie would have dreamed of, you know, if he knew this formula, because there's a slope. M squared is the invariant mass squared. It's all the hadronic masses, and it has a term in N, which is the principal Coulomb number, the number of nodes, if you like, and J plus L, the angular momentum term. But what does this mean? It means, in fact, when you look at the slope of the Reggie trajectory, it's the same for both N and L, identical, which is what you see throughout the particle physics, both for the mesons and the baryons and for the tetraquarks. It's actually, I'm lying about the tetraquarks. We don't have enough of them to see, but as far as we can tell, they're the same. Okay. So we're using this dilettante profile. We're using that matching Z to zeta. We get this formula. And then we notice, in fact, a miracle, that when this term J minus 1, which comes right here from the ADS5, it's negative for the pion. It exactly cancels the terms which are positive from this guy and this guy. So this is actually the miracle why the pion comes out to be massless. And as far as I know, this is the first time anybody's ever seen a bound state with massless eigenvalue. Now, of course, when we put the quark masses back in, we'll get the pion mass. But this is really astounding that you have a hadron which has got form factors and structure functions and everything looks right, but it's got zero mass. And it's invariant mass. It's the one that any observer would see in any Lorentz frame. Okay. So you plot the spectrum. You see these Reggie trajectories, m squared versus L. And as you go up in N, you get the right slope as well. Okay. So to universal hadronic features, I mean, everybody has a light front kinetic energy contribution. You can do it that way. A universal light front potential energy. This is the virial theorem, that in fact with a harmonic oscillator, it's generalized to the front form. You get the same contribution for these two guys. And then there's constant terms which are spin related. And here's sort of a simple formula for how it works as you add diquarks in. So you get every hadron has a contribution from the kinetic energy, from the light front potential energy, and the spin terms. And then you add in, of course, the mass term, m squared over x. But what's interesting is the virial theorem, right? You think that's sort of a non-relativistic idea, but it's true here, too, in the front form. The potential energy and the kinetic energy are the same as far as their contribution to the mass, the invariant mass squared. So we have a relativistic frame-independent equation. The QCD mass scale appears. It reproduces all sorts of spectroscopy. It reproduces structure functions. I'll come back to that, form factors. zero mass pion, Reggie-slope, same for N and L. And also, I said this yesterday, Friday rather, if you look at the different Reggie trajectories in L, now each of them actually have a hidden L plus one, just to emphasize, it's a little confusing. L refers to the lowest of the two. That's sort of the convention. That's what we've done in atomic physics too. When you refer to the orbital momentum of a proton at a bound state, L means the lowest guy, but there's always another one. And then, but they never cross. Reggie trajectories from this theory go on forever. It's not what a lot of people believe, in fact, that the vacuum breaks the chiral symmetry, and therefore at high mass, L and L plus one, the baryon doublets have to cross. They do not. There's no such thing here. All right, and then you can extend everything to heavy quarks, and then, of course, compute observables, and I'll review a little bit of this. Somebody asked this question Friday, which is an important question, is that we're familiar with the linear potential for quarkonium. You know, if you do heavy quarkonium, the confinement potential is linear as far as we can tell phenomenologically, right? You fit that to orbital spin terms, and then you have one confinement potential, and it's linear. But in fact, that is the same as the harmonic oscillator potential for light quarks. The difference is simply kinematics. The way to think about it is that the mesons in light front is like a Klein-Gordon equation. What appears in the Klein-Gordon equation is the square of the potential. So that's why you get this guy is basically the square of this. So in fact, if you just do the algebra, you compare the algebra of normal kinematics with light front kinematics, and you go through the algebra and compute the potential for the Klein-Gordon equation, which has got this v squared term in, then it turns out that you have this mapping I just mentioned between this guy and this guy. In fact, you can even predict the constant c, which is often called sigma, and it comes out right. It's the right number that you see from the quarkonium potentials. Now, so one of the wonderful things about the ADS-5 approach is you get the light front wave functions of the hadrons, and for the case of the pi and the rho, it's just this beautiful Gaussian shape, and you never get k-perp alone. It's always coupled to k-perp square over x1 minus x. And when you integrate this over k-perp, you get the distribution amplitude of the pion or the hadron, and it has this magical form square root of x1 minus x. This is the non-perturbative pion distribution amplitude. Of course, it evolves by herbal evolution, but that's later. What you start with is the bound state problem, which is actually just starting with, in fact, the bound state of a quark and anti-quark. You get this beautiful wave function in x and k perp squared, a Gaussian shape with a shape which changes with x and 1 minus x. That's pretty interesting. Okay. All right. So also what we're saying, in fact, is something that we normally don't discuss. You know, people who work on QCD, they usually are interested in getting the mass spectrum right so they construct a model. But rarely do you actually work on a theory which has both the potential, the spectrum, and the wave functions simultaneously, right? So you want to make sure you get the complete spectrum in N and L, but you also want to make sure that you get the wave functions underlying it. So many times people just look at spectroscopy without looking at dynamics, and this controls dynamics. So here's an example. If you start with the square root of x1 minus x contribution, you can use a formula that Pagenite derived for the transition form factor between a real photon and a pion. So it's gamma star gamma goes to pi 0 is the experiment. And it's measured at Bell and Barbar. And as far as we can tell, the data is consistent with the prediction, except for these points up here, which is Barbar. They must be wrong, right? So, you know, somebody's got to keep repeating this to make sure there's no problem at all. But it looks a lot like the prediction directly that Cal determined. I mean, yes, I'm sorry. Yeah, it definitely. Yes, please. Yeah, so these are these points up here are contradict the prediction, but they also don't seem reasonable because they contradict scaling laws too. See, because q squared times f should be a constant if you believe in dimensional counting. So, and every other hadron form factor of Bayes County rules. So
So which is the line to F5? Is the dashed one? No.
I'm not sure if I understand. This is 2f pi. If this thing goes to infinity to 2f pi at infinity. Is that what you're asking?
Yeah, I was wondering which one of the lines.
Oh, I'm sorry.
F pi actually, because you have the dashed
Yeah.
one, the solid one, and
Right.
these are a little bit different.
Yeah, they're different because we actually tried in this paper to actually see if we could estimate the higher twist contribution. And that comes from actually, the way I remember it now, it's been a while, is that you can relate to the Gelman-Low procedure, the gamma mu matrix elements and the gamma 5 matrix elements. So you need another wave function, which is actually pseudo odd. And this, it's chiral odd. And so when you invent that wave function, which is not predicted here, you actually can see a higher twist correction. So it's a minor effect, as you can see, between these two guys. Okay. So if you solve these light front equations, then for each of the hadrons, you see this beautiful results that the light front wave function peaks at x of a half for heavy guys like ellipse C and A to B, because that's just intuition. What it is really is that you get to the non-relativistic form, and in the super non-relativistic limit, x is just the ratio of masses. It's a half. So that's all you get. But then what the deviation from a half, that's the light front variable, light x variable, it actually varies then around the key variable. And so then here's a case very asymmetric, where in fact the heavy quark carries most of the x and the light one carries the little one. So this is just what you expect from intuition. Also, I'd like to emphasize that what you're really doing is minimizing the difference of rapidities. In a hadron, the bound state likes to keep all the particles moving at the same rapidity. That's basically velocity. And the equal rapidity is the same as the x variable going like the square root of m perp squared plus k perp squared. So in fact, you can think about how x works by just knowing this formula that they all have the same rapidity, and then just plug that in, and you get actually a very good characterization of these forms. But the underlying principle, which I think actually Feynman was the first to emphasize, is that nature doesn't like states which are far away in rapidity from each other. All correlations are close in rapidity, because you can't, if one particle is far away in rapidity, you have to transfer that information by step by step by step by step, and it's lost. That's Feynman's intuition. He said if you look at the spin of C quarks very far away, they can't be correlated with the proton spin anymore because it's too many splittings before you get to it. However, if you're close in rapidity, then of course you get the correlations. I showed, of course, this Friday. This is a fantastic result, I think. The anti-de Sitter space gives you immediately this form where kappa is determined, say, by the proton mass. Basically half the proton mass. So this is the Gaussian shape you get, and it comes directly from going back to anti-de Sitter space and then using this wonderful connection, the dictionary, and you get this form. Now in this case, we're talking about the Bjorkian-Sumrall definition of the running coupling, which is a very elegant definition, but it's normalizes to 1. You don't have any choice here. So you're not predicting the normalization from anti-de Sitter space. So assuming this normalization, then you get this Gaussian shape. So this looks pretty good, and the kappa of 0.54 is really the best fit to all the Regge trajectories. Now, then what we did, Duer de Terman and I, is we said, let's actually assume that this Gaussian connects as smooth as possible to the measured coupling at the short distance domain. And so people have measured an MS bar scheme. You can tell I hate MS bar because I think it's so artificial. People are so confused by it because it's so made up, it's so artificial that only humans on Earth would even think of such a thing. But nevertheless, since everybody uses it, I'm forced to use it because we know how this thing goes out by 5 loops in MS bar scheme. But you could do any scheme. Anyway, in any case, we connect with Q0 to the MS bar scheme, and we go, in fact, from kappa to lambda MS bar right here, and it's close to the world prediction. Yeah. But this scale Q0 is pretty neat because it tells you the connection where you go, in fact, from non-perturbative to perturbative physics. I didn't say this, is that the way you derive this is by matching the magnitude and the first derivative. That's how you actually make the connection. The second derivative is not continuous. It jumps, and this is a turning point. So this is really not an analytic connection. However, it's as close as we can get. So this is what we do. So there's some model dependence in this thing, but it's really shows, in fact, you have a consistent description of what running couplings look like in the soft domain and connecting to the 5-loop answer we know in the real world. So Q0, since it's a division between non-perturbative and perturbative, it's the natural starting point, the starting point for de-Glapper-able evolution, and this is what we've done in subsequent papers. So I'll just mention this, like I've said it before, that actually if you start out with the Drell-Yan-West formula and you put it into coordinate space here, zeta and x, then you get this formula right here. And then it turns out that you go to the Polchinski-Strasser formula, and by matching this one identity right here, it turns out to be exactly the same as their formula for the form factors. So I'm not going to go through the algebra, it'll take a half hour, but the point is that that's one of the ways you see this remarkable connection between anti-de Sitter space and our world. And let me emphasize, the Drell-Yan-West formula is precious. It's just the overlap of the light front wave functions. There's nothing else like it. As I said earlier today, the beta saltpeter requires an infinite number of cross-graph kernels to get there. So it's really very difficult to use beta saltpeter for form factors. You can do lots of tricks with it. However, for this case, it's terrible. And of course, there is no formula in instant form because you have to know how to boost from P to P plus Q, and you have to put in these amazing graphs where the current comes from the vacuum. So anyway, this identity between the Polchinski-Strasser formula and ADS and our world in Drell-Yan-West is remarkable and key. So when you calculate the pion form factor, this is space-like pion form factor, our model just gives this red line. But in fact, it turns out this is one of the few cases where the hard wall doesn't give the wrong answer. So I just show this too. But of course, they both have counting rules built in. Now, there's another thing. Now, the Drell-Yan-West form is exact. But if you think about the time-like form factor, you have a problem. Because there's, in E plus E minus 2, so pi plus or minus, there's a rho meson pole, right? Now, if you think about the Drell-Yan-West formula, it's there, but it's a sum of infinite number of gluons are going across. So it's not simple. So in fact, there's a way around it. And it's a lot like the connection to the Heisenberg picture for currents and the interaction current. You can go back and forth. And the Heisenberg picture, you actually are addressing the current. So this is what we've done. So we address the current. And the address current includes then the diagrams that are in the Drell-Yan-West formula, but now they're summed up in another way. So in fact, this goes back to Gregorian and Radushkin and Gita Teraman and myself, where in fact you actually calculate a dress current, J, just from the same equations that we were using before. And so this equation actually modifies the, for large Q squared, there's no variation, but for low Q squared, you actually derive the poles in the time-like region. So this is what happens. So, this is the trouble with lecturing, and I know I'm supposed to go slow, but the trouble is that each of these topics, would take an hour to explain, so I'm stuck just summarizing it. So yeah, I apologize. But what happens is you get automatically pole structure for the form factors on the time-like side. You see, in fact, it's the analytic formula, but you get formulas like this. And the formulas that have poles at rho prime, and rho double prime, and so on. And so you actually do get, in fact, these structures like the rho and the rho prime. However, it's a cheat because we don't know how to put the widths in. We can put in the rho prime at the right mass, but not the widths. So this is really a cheat because what we've done is we put in the width in the standard formula just from phenomenology. So that's how you get these curves. So here it is a little bit better. The space-like side, it's what I showed before. There's not really any change, but in the time-like side, because of the poles in the dress current, you get the poles in the rho prime, and so on. So this is a game we're playing, but there's also another parameter, which is the percentage of rho prime, and so on. So, it's not the, you guys are the future. You can do this better, but this is what we've done. Now, in general, when you put this dress current in, you actually get these beautiful forms. Here, q squared is minus 4 vector q squared, of course. And so you get, for a particle with 2 constituents, you get this. Particle 3 constituents, you get this, and so on, because counting rules are built in. But not only that, what's built in is that the mass scale that appears every time you go through another resonance is right there too. So it's actually a generalization of the Saccharide formula. Saccharide said the proton form factor is the product of 1 plus q squared squared. Well, that's nonsense, because that has a double pole, the rho. I don't know why people took that to be serious. This has the right analytic structure. It's got a pole, rho prime. It's got the right counting rules. This is sort of a mystery to me, how many years the Saccharide formula sort of existed, and people didn't say, wait a second, there's no double pole. But that's what he did, Okay. But anyway, so then you can go on to any number of constituents and predict the form factor. So now going back, we have the meson-baryon tetraquark symmetry in the fourplet. Where did it come from? It came from this Fubini-Rabinovich idea that you add to the square root of the Hamiltonian the square root of the special conformal operator. And when you do this, you immediately generate the confining potential. So here's actually the equations I prefer to show in this slide. You reproduce the meson equation, and the baryon equation is right here. It's very similar. The difference between the baryon, which is really a quark-diquark in this picture, it's got the right scaling laws and everything for 3 quarks, but it organized itself in that way. But then you see, in fact, that L appears here, L plus 1 appears here. So in order to make the identification, you have to actually identify the hadrons, which have 1 unit of L higher than the baryons. And that's actually the prediction. There's no other, that's what you get. It's not like, let's make up a rule that we add 1 unit. It's not true. That's just, you get this. And also you get equal weight for the 2 contributions. And this is true for any fermion J. Now there's another way to get this. In fact, Guy de Terman and I, before we understood superconformal algebra, we were just trying to extend our work on mesons to baryons. And the logical thing to do was to introduce a Dirac equation. And so we introduced a Dirac equation, which actually, when you square it, gives the right Klein-Gordon equation, and so on. And so then we ended up with basically the solutions that you get from the superconformal algebra. So another way to get to these answers is you start with the Dirac equation, and you make sure that when you square it, you get the Klein-Gordon equation, which is the same as the meson equation. And that's what we did that for a couple of years, and so until we discovered the papers by Rabinovich and Fubini and understand how to do it. And then the payoff is not only the baryons, but the tetraquarks. So then when you apply the equation, either from this Dirac equation approach or, in fact, superconformal algebra, you get these Regge trajectories. And for the nucleon, I'm showing it in N and L, and so on. And then you get this degeneracy between the pion trajectory and the nucleon trajectory, but they're just off by 1 unit of L. It's actually not perfect, but it's there. In the case of the rho trajectory and the delta trajectory, they're really right on top of each other. It's remarkable. Mesons and baryons, and this is supersymmetry in the spectrum. And so then I cited before the work of Nielsen, where she just went through the particle data book and just identified, just going across, where the tetraquarks are. Now, you're not sure what you're doing, right? You're matching the masses, you're matching the quantum numbers. The tetraquarks have isospin. They're not glue balls, because glue balls are isospin 0. That's different. And anyway, it is, you predict then all these states, and you predict their spin, because you can have both spin 0 diquarks and spin half diquarks, and so on. So there's notation, the bracket is spin 0 diquarks, and the parenthesis is the spin 0 diquarks. Spin 1 diquark. If you have 2 quark with the same flavor, they have to be spin 1 by Pauli statistics. So that's built in. So then you go through all the states. You never get a matching state to the lowest meson, because you have to start out matching the L+1 meson. And that's how you go through and you get this go across. Now here, distinguishing meson glue balls and tetraquarks. So if you do E plus E minus goes to, let's say a K minus is one example, and you can make a tetraquark over here, the scaling law will show 4 beautiful quarks in the scaling law, because you just look at the amplitude, you take number of constituents minus 4. In this case, it's 2 plus 4 minus plus 2 minus 4 is this 1 over S squared. It has exactly the right fall off, just like the proton form factor goes like 1 over Q squared. So this is a way to test how many constituents there are in this system. Now, if you you want to look for a glue ball, you'd have to put a isospin 0. Isospin 1 is okay for this case, a meson, and then go against the glue ball. So people should be doing this. They should be going through the data carefully and looking, in fact, which states could have just 2 particles and which states have 4 particles, which have 3. 3 would be quark-antiquark gluon. Maybe this is the way to find things. I'm surprised it's not a gigantic literature, just one after the other searching these things. But again, just to emphasize, the glue ball, it not only has to satisfy 2 constituents, but it has to be isospin 0. Otherwise, it's not going to work. Okay. So here's more comparisons with the real world. When you put in this modified current, you get this rho squared, rho prime squared, as I said before, and that looks on the space-like side for the proton form factor pretty nice. In real world, there's also evolution here. There's the herbal evolution, which will bring this down and goes down in high Q squared. However, just from the simple formulas, you get a fairly good representation of the data. Now, there's actually two form factors for the plus and the minus. That's the L and L+1 states. And then the connection between them is that you get JZ. You also have to go through the spin statistics, spin flavor symmetries, and so on. In the end, you end up with the F1 here, and the F1 of the neutron involves this correspondence. So you go through this and you make prediction. Here's the same thing I showed before for Q the 4th F1 proton. This is the Pauli form factor, which falls 1 over Q squared faster and looks a lot like the data. The neutron one looks very close to the data. However, these points are far off. And maybe it's because this is an old plot that people have already corrected this. But this is the Q to the 4th times F1 neutron. So here's a little bit more comparison, the proton Pauli form factor. And this is actually more recent work by Gucci, Lubavsky, Schmidt, and Vega. And they have taken our formulas, they've computed the d-quark form factors, the neutron form factors, and so they don't see a discrepancy. So maybe I'm a little confused what happened with our data points and theirs. I don't know. Oh, they did. Okay. All right. So also there's another work here by Nitika Sharma and so on. Looks a lot like the data. This is very similar. And then we've also put in, we've calculated Q the 4th F1, Q the 4th F1 neutron, Q the 6th F2, and so on. So we've been doing more, but we've actually added in an arbitrary 5-quark Fox state contribution to make this look perfect. So, that's model building, but you're starting with the same underlying valence state and then putting in the 5-quark extra states. So I've already showed you this. All right. Now, when you do the case of the transition form factors, this is a nice example. Here you're going from a nucleon to the nucleon star. This has been a half, this has been 3 halves, for example. Now, the form factor vanishes at Q squared equals 0 because they're orthogonal states. The current can't connect a state which is orthogonal. However, after you put in the Q squared, which is automatic, then you get 3 poles in the denominator. So that's the prediction. And that's not great, but this is what you get. You get the right fall off here, but these points are a little bit low. Anyways, this is what you can start doing, though, to get transition form factors and how you can play with this. All right. And here again is the end-to-end star, together with the spectroscopy. So a little bit more on the superconformal algebra. The mesons are quark-antiquark. They match the baryons if you displace by 1 unit. The baryons are quark-diquark. Some of them are quark scalar diquark. Some are quark vector diquark, and so on. And they all have, then you get the tetraquark contributions, universal Regge slopes, and you get this equality between the kinetic term and the potential term, and then the contribution for the other states, and this just summarizes what I said before. So this is really and chi discounts the number of diquarks, basically, and you just get this rule. So other features, the wave function has both L and L plus 1. It's like upper and lower components of the Dirac-Coulomb equation. Jz is conserved always. It's just the end of, you just add Lz plus Sc. The proton spin is carried by the quark orbital momentum. So let me emphasize that point, that half the time the quark is aligned, spin is aligned with the proton spin, half with Lz equals 0, but half the time it's aligned opposite with Lz equals 1. So that means, in fact, that together, on the average, the spin cancels out of the quark, leaving the orbital momentum to carry the proton spin, the plus a half proton spin here. So this is not exactly what you see in the real world. However, after you apply de Glapp evolution, you're close to this. I mean, nobody contradicts this as far as I can tell. This is the natural starting point for de Glapp evolution. See, because we always look at these sum rules and try to deduce the spin, by very indirectly, and it's at high Q squared. So you're never really looking at this directly. However, this is a fantastic starting point. It says life is as simple as it could be. My philosophy is that nature may not be as complicated as we want to make it. This is really an example where the spin sum rule is really trivial in the non-relativistic, in the non-perturbed region. Excuse me. So here's another case where you start with when you want to look at double charm baryons. So here's a case where you start with a first excited state of the meson, and then what you do is you go across to make actually a scalar diquark, like this. You put the C with the D. If you put the two C's together, it has to be a vector diquark, so that's going to be a higher mass state. So then you go from 3525 to 3520. And then you predict another tetraquark right here, also at 3520. Nobody's found this state yet. So this would be a tetraquark with a CD diquark, spin 0, and an anti-C bar, and then any Q bar. So this would be a whole range of tetraquarks with 2 charm quarks in it, one with a C and one with a C bar. But this guy has got 2 charm quarks. One of them is hiding in the diquark, and the other is outside. This is a 3 bar. Together they make a color singlet, and together they make the bound state with the same mass as the meson with 1 unit of orbital higher. Okay, so that was our prediction. And then you look at the Selex data, and at 3520, wow, there's the double charm baryon. They see it in 2 different decay channels. Hard to believe this is wrong. And they're pretty happy with this. That's what their prediction is. Physics letters and so on, the Selex collaboration. I can't remember the statistical significance. I think this is like a 5 sigma. This is 3 or something. Together, they're very significant. And they have the right to the expected decays and so on. And so here it is, another version of this thing. All right. Well, they showed actually another, what this is, there's another state besides the one at 3520, there's another one which is higher, 3780. And that could be 2, because you expect a whole progression of them. There'll be excited states in L, excited states in N. You can change the diquark from spin 0 to spin 1/2. There's a lot of possibilities. It'd be unlikely you don't see more. Okay. But however, how do you produce them? Well, the proton's got intrinsic charm. It's got intrinsic double charm. How do I know this? Because you see double J psi production at high XF in A3. I'll review that maybe a little bit more tomorrow. But anyway, what is true is that you have these Fock states. And they're complicated Fock states, but they're all moving at the same rapidity. So then what happens, you can have the case of a C and a C and a D all moving together. And it happens to be this one's in a spin 0 state. This makes the state we want, the 3520 CCD. And then there's all the other states. If you look at the other, you look along the way, you'll see associated productions. You'll see, in fact, other states with there'll be my 2D bars, all sorts of interesting states. Okay. And Celix then sees this thing. Now they see it at high XF. That's actually where their experiment has sensitivity. They maybe find that surprising that you'd find 2 charm quarks at high XF, but that's exactly where the LHC, first of all, the people found the lambda C, the lambda B, all at high XF. Celix has done extensive studies of the lambda C with different beams, always at high XF. That shows there's 1 charm quark out there. Then Na3 shows there's 2 charm quarks out there, actually CC, C bar, C bar. There's no problem. And this state here is actually the state which has got minimum off-shellness. It's the state where all the particles are moving with the same rapidity, and that's the state where you get coalescence of particles with the same rapidity into the hadron. So my philosophy is a lot like Feynman. This is where you should look. You should look for the case where the particles are already coalescing at the same rapidity. Yes, go. I'm sorry. Oh, this one's above 0.5. No, what is it? Sorry. Oh, XF is the light front X, if you like, of the sum of the 3 quarks. So if we add up together 0.3, 0.3, 0.1, you get way out in the high XF, and that's what you see. So XF is the same. So XF was first of all thought about in the center mass system. But when you translate it back to the light front, it's exactly what we were talking about, the first approximation. It's just the adding the light front X's. So good. Remember, the charm quarks, I showed a plot of that yesterday, or Friday, for the EMC collaboration, which actually has a huge contribution of point for each charm quark at 0.45. Q squared is 0.42, Q squared is 75 Jev squared. Why is that? Because the proton likes to be in a CC bar UUD configuration, but they all want to be at the same rapidity. That's where the wave function is maximal. And therefore, the charm quarks, the X goes like the square root of M squared plus K perp squared. The charm quarks have high X. So it's hard to you have to get used to this point, that equal rapidity is where the heavy particles have most of the X, just to make the rapidities equal. So this is the natural domain to find the double charm baryon. There's nothing wrong with this. But then there's the fact that actually, so here it is again, CCD, it produces it and so on. Here XF is about 0.33 is the average where they see it, but it goes all the way out. Okay, but now comes the problem. So they have 2 decay channels that LHCb sees a state at 3621, 100 MeV higher. And so LHCb says, you guys at Celix don't know what you're talking about. It can't be that there's a 3520 because our state, 3621, would decay to it by radiative transition. That's a serious problem. If the 3621, which they discovered, is actually can decay by a photon down to the Sugg sky, they both got CCD, I'm going to say. That's a problem because then you never would see the weak decay, which is the way LHCb discovers their state. However, I looked at the colleagues. You can't see their names here. But anyway, no. And we studied this and tried to estimate the rate of decay, and it's actually suppressed by 7 powers of 100 over m's side. They're so close together, and the mass scale is so small. So the size is so small, you don't get this. But people should be looking. Everybody should see both. There shouldn't be one state and not the other state. So we think, in fact, that possibly that the heavier one is actually the spin 1 diquark, not the spin diquark, spin 0 1. It's possible. There's so many possibilities, but you can't exclude one experiment just because you don't see the same mass, because there's so many candidates. That's what I'm emphasizing. Okay. All right. Okay. Now here, let's see. This is from you. So this is Rinaldi Vento and Arava. They're using something like our approach, ADS5 and so on. You can explain it. which actually gives a glue balls. But they haven't really plotted the Reggie spectrum yet and so on, right? That's fair, right? To see, in fact.
The game is wrong. I said the group spectrum, there are no data, but there are latest data. And it seems that there is a linear trajectory. Yeah. The problem that we face is that if you try to solve with the scalar, you don't get the square. So we try to solve it as considering the glue ball as a graviton. So we solve not the scalar equation that we find here, but the Einstein equation. We define the gravity in
Yeah.
use the kiloton, and we find numerically this is not unequal linear trajectory. We didn't know that, but we just try to do it, and we find that we can put the green with the data.
So the data points is lattice estimates of the glue balls. That's what that is. Yeah, right. And
Put the scalar
right.
and the tensor, and then we see
Right.
the DC.
And the green line, just to remind me again, the green,
There is also the art wall model.
that's a hard wall model that you
But
described
you
today.
get the linear trajectory also in the art wall model, but we know that the art wall model does not work with pi or mesons.
Right.
So we would like to see everything the same.
Okay. So continuing on, so why are we interested in this thing? Well, there's chiral features, all sorts of features. First of all, everything is boost invariant. Doesn't matter what the Lorentz frame of the observer is. The vacuum turns out to be trivial. And I'm going to show you a little bit about that. It's coming up in the next hour. And this is that there's no so-called condensates in the vacuum. Craig Roberts mentioned this. Massless pion, the hadron eigens, so that's something like chiral theory. Hadron eigenstates have light front components of different L, so that's the proton case, for example. It's got both L equals 0 and L equals 1. This is confusing because we never think of it that way. We think of the proton, it must be an S state, right? It's the lowest state. That's not true, right?
Sorry, you said the massless come out, the pion come out.
Only for zero quark mass.
Right.
Yeah,
Because then you plot the.
that's right.
Defeat
I mean, everybody believes that should be true, but this is the first time where this comes out analytically. Yeah. So the proton then, as I emphasized, got these two components. LZ's average is a half, the quark spin is 0. The proton is its own chiral partner. So this is also different than we're used to. We usually think that you go to L and L plus 1, two different Regis trajectories. No. Each state has different L's, just like in the Dirac-Coulomb equation, the upper and lower component. Parity is not broken, but they're both there. Okay. Now what we do is we label the state by minimum L. So we don't mention always that there's an L plus 1. That's the lower components, but they're there. All right. The minimum L is all that matters when you look at short distance. When you look at an operator that's at short distance, you always use the lowest L because the wave function vanishes as L to a power. Okay. And then the way anti-de Sitter space works is this: you match the interpolating operator twist at z equals 0, which is where the quarks are on top of each other. But then, as I emphasize, there's no mass degenerate parity partners. You don't see another state which is going to converge. Okay. So I think I said all this here. Again, 0 mass pion for 0 quark mass, same Reggie trajectory, and so on. All right. So there's other states in this world. So one, I just want to mention these type of states. You know, you can have a quarkonium state bound to a nucleus. And it works just like in QED. You can have two glue interactions, which are like the QCD version of van der Waals forces. So you can always have a J psi, an upsilon, bound to a nucleus through the attractive multi-gluon interactions. There's no valence quarks in common here. You know, so it's not quark exchange, nothing like that. It's really got to be the gluon exchange that does it. The potential is doing it. But it's not a bound state in the normal sense. It's a molecule. So that's true. But now, so I wrote a paper with Ivan Schmidt and Terramana on this and so on. However, Manahar made an important observation. He says, this has to happen for a heavy enough nucleus. The reason is that when you solve the non-relativistic problem, which this is, the kinetic energy term is p squared over 2m. And as you go to heavy nuclei, the kinetic energy term goes smaller and smaller. The potential always dominates. So there's no way you can avoid these nuclear bound quarkonium states. And that's interesting. So, experimentalists have a lot to do. So here I showed an example of a proton with a deuteron target making a bound state of this guy. And then you look out and you'll see, in fact, the heavy quarkonium come out. You can do this with photoproduction. You can make the J-psi and see the gluon interactions and so on. And you can see, in fact, the bound states and the intermediate states. And so that's good. Okay. And here you are, in fact, at the final state. So this has got the advantage here. You start with a deuteron, and then there's a proton spectator. The neutron and the J-psi can bind together beautifully, and you can see, in fact, them there. This is the natural way at JLab to see nuclear-bound quarkonium states. This one's the simplest J-psi nucleon. All right. So I wanted to show this, which I love. This is the octaquark. And I'm sure nobody in this room has ever heard of an octaquark before. That's an 8-quark object, actually 6 quarks, one more quark and one more antiquark. How can that be, right? And you can form it by taking a photon, virtual photon, could be electron here, and a deuteron, and this could make the octaquark, which would be UU, DUU, DCC bar, really. Is there I think I made a mistake. It should be two D's here, not 4 U's. It's 3 D's and 3 U's. I'm sorry. Right. I'll fix that. Okay. Actually, hexaquarks were first mentioned in 1964 by Dyson and Zhang. There's also all sorts of interesting states, which have all sorts of interesting quantum numbers. You can make hexaquarks. You can take 3 diquarks and put them together. Each of them is a 3-bar. Then 2 3-bars make a 3. The 3 goes with a 3-bar. There's zillions of possibilities. Now, to me, it's funny that we haven't found them. And apparently what they are is just simply molecule-type states. They're not really bound states like the proton and so on. So this is one state to look for. Nobody's really done it, but JLab could find this. But here I want to come back to this octaquark. So Alan Krish wrote a Scientific American article. He was the head of an experimental group I think at Argonne at the time, where they measured polarized proton-proton scattering. And they measured it like at RIDS of 5 GeV, that's PLAB at 12.7 GeV, and they could polarize both the proton in the beam and polarize the proton in the target. So they could do really the ultimate experiment. So then what they did is they actually measured the case where the 2 protons are parallel, going up versus going down. And what happens is that they saw a cross-section here, then for a long time there is nothing, and then suddenly it went up. And the only explanation I know is actually the baryon number 2 octaquark. So I'll explain that and so on. But in his Scientific American, he said the QCD must be wrong, that no QCD could never explain this peak and so on. And he said the best explanation he had was onion skins. That was Krish's explanation. So that was fun. Okay. So here's what we found, in fact, is here the ratio of spin parallel versus the other is 4:1. Oh, I made another mistake. It's parallel versus anti-parallel. I said this wrong before, sorry. Another error in the slide. Okay, anyway, he found, in fact, that the parallel thing suddenly becomes, at this energy, 4:1. He could not believe this. However, if you put in a resonance, UUD, CC bar, that's 2 protons, it's the right thing, with an extra CC bar, the mass is 1 plus 1 plus 3, and you get 5. The problem was that he did the experiment before charm was discovered. If he had thought about it, he'd say, my God, there's a new flavor. And we're seeing at the threshold of resonance. And that actually explains the data. And you can actually explain, in fact, this data, the experiments by Crab et al., and it's pretty remarkable. And it's just elastic scattering, this incredible rise. So what Gita Teraman and I did is we calculated basically this graph. We said an extra CC, 2 charm quarks come in, they make an extra CC bar, the 8 quarks resonates, we put that into the scattering amplitude at 5 GeV, and we were able, in fact, with the quantum numbers of putting an S wave in here, with the 5 GeV guy, you actually explain all the data points of Krish. So here we are with a new world of heavy quarks. You know, there's nothing wrong with that. And this, of course, the precursor of bound states of charbonium to hadrons, to 2 nucleons, for example, the deuteron. But also, to emphasize the point, a surprising point, when you put this state in, it turns out that the Clebsch-Gordon coefficient is 100% that you get this correlation this way, not this way. Okay. All right. So there's new QCD physics of the charm thing. You get enormously large charm production. Well, it's not huge, but you get octaquark resonances. GSI could be looking for these things. You can produce J psis, lambda CDs, and so on. All sorts of interesting physics could be done. Okay. All right. So then, so the deuteron, you can make a lepton scattering on a deuteron and make this state right here too again. 3 U's, 3 D's, you see bar this time, it's right. All right, so let's see, I've said this. I think what I wanted, is it now time for an hour break, for the break? I started.
Let's say we break just at the moment.
Yes, now. Yeah, I could use the break. Okay. Okay. Right. Oh yes.
I was a bit confused with your plot on the bar. I mean.
Okay, I'm going to continue. Okay. So I like to think about this like the Bohr atom. You know, we start out with something that's very close to reality, and then later on you learn about the lab shift. Oh my gosh. The hyperfine splitting, you learn about all the different corrections, vacuum polarization, and so on. But, you know, we've never had a starting point for QCD, and that's what this is why I'm emphasizing this subject. And it's relativistic, frame independent. We have a QCD mass scale appearing in an unusual way. We have this unique confinement potential. You reproduce the spectroscopy in an amazing way. We've never had anything like that. And dynamics, and I'm going to come back a little bit to that. 0 mass pine for 0 quark mass, same Reggie slopes. Splitting in L never goes down. It's always parallel. All sorts of phenomenology. And you can extend it to heavy quarks. Just put the mass in. So you get dynamics and spectroscopy. That's important. And we're using Poincare invariance, quantization of fixed light front time. Dirac would love this if he was here. Causality is there, light front holography, single scale superconformal algebra. Oops. Okay. So I've said all this. Also counting rules and the connections now between the hadron mass and whatever scheme you pick, lambda miss bar. I'm going to explain next lecture tomorrow how to go from lambda miss bar to any other scheme a little bit later. All right. Okay. I've showed you how you partition the proton's mass, equal contribution for the potential kinetic terms, the role of quark orbital momentum, the quark-diquark structure. The proton is just quark-diquark. Actually, Craig disagrees with that. He thought the diquark is both spin 0 and spin 1. We don't have a role for the spin 1. Baryon Reggie trajectory. So somebody's going to have to make a choice, you know, experimentalists. Mesonic super partners. We have also the tetraquarks. We have the wave functions of the proton and so on, form factors, non-perturbative, perturbative transition, and this dimensional transportation. So I've said all these things here. I could have plotted this. But here, the quark mass contribution is basically just the expectation value, m squared over x. And here's the wave functions. I should have clicked before. All right. And then I told you about light front perturbation theory. We discussed this today a little bit. What are some of the advantages? Well, the reason why it's interesting, other than, Feynman is maybe more efficient. However, every diagram, you have propagating particles on their mass shell. They're only off their invariant mass shell. Everything is physical. Unitarity is explicit. Just like Feynman rules, it's frame independent. There's only a few time order diagrams, only the ones which are really, in fact, the particles move plus, with positive plus momentum. Jz is conserved at every vertex. You're already normal ordered. One of the mysterious things about Feynman rules is you're instructed to eliminate the vacuum graphs. You either say, well, you normal order, or you divide the vacuum graphs out in the S matrix. Here, there's nothing like that. There's no artificial rule like this. Unless you do that for Feynman, you violate causality. But for us, it's built in. There is no vacuum graphs, period. Okay. Renormalization. Now, people ask about this and so on. If you didn't know how to do Feynman renormalization, what would you do here? It turns out it's straightforward. And I wrote a paper with Brodsky and Swaya where we did the electron G-2 to 1 loop, 2 loop, and almost all the 3 loops, and before we got exhausted. But anyway, the point is that you simply have the same diagram and you subtract that diagram with a different denominator, and that reproduces the mass renormalization, and so on. So it's really straightforward. It's basically Beta's idea. When Beta evaluated the lamp shift, he had to take the self-energy diagram and subtract the mass renormalization. This is the same idea. But here it's systematic and easy to do. So that's called alternate denominator method. So, and we tested the 3 loops. Then there's the Park-Taylor rules and amplitudes. So Stasso's done a lot of work on this, and so on. I've done work with this with my student Kelly Chu. You actually have powerful things. If you're looking at 2 gluons, go to 6 gluons, and so on. It tells you right away which amplitudes are 0, which are non-zero, and they're easy to compute. So this is perturbation theory. But the point is that at every vertex, you only change orbital momentum by 1 unit at most. That's a renormalizable theory. So you immediately see how Jz conservation works, and you can see which helicity amplitudes can possibly survive. And that's there, all right. And then there's hadronization at the amplitude level. I'll mention this a little bit later, that actually this is the way I think we should try to calculate how hadronization works. You start out with E plus E minus, goes to multi-quark and pairs and gluons. How do they convert to hadrons? The light front wave functions take you from the off shell, that's off the invariant mass shell, to the on shell. And that's how you work. Now, given these light front wave functions, you can compute virtually everything. And that's the whole story, right? There's a gigantic literature on this. So this is, just an introduction. But basically, just like the form factors, they're involved in light front wave functions. And you just square them and do different operations, and you get these different observables. So there's a long list of things. You can also calculate the Wigner's function if you want, but that's not necessary here. You just do it directly. Okay. So anyway, this is really generalized transverse momentum distributions and so on. They're pretty much all there. And let me just go back for one step. I'm sorry. But I do want to mention here, and I'll come back to this, the Sivers effect should warn you. I discussed that. We'll come back to it. The Sivers effect tells you this is not exactly right, because all we're getting is the information from the wave function in these forms. There's final state, initial state interactions which appear in the experimental data. So you have to be careful. So aside from that, you get the input from the wave functions. All right. It's the same for atomic physics, by the way. Atomic physics, you could get any atomic structure you want from the wave function, but there's still initial state and final state interactions you have to worry about. Okay. So light front wave functions are key. Please go ahead.
So where does the B perp come from, the light front wave function?
Yes. So remember the wave function is a function of zeta, and zeta squared is B perp squared x1 minus x. Remember, so the zeta squared is the analog of the transverse separation. but it's the radial variable. It's the one that's actually spherically, not spherically, but in the light front, it's the symmetric one. It's got the right three-dimensional symmetry. So yeah, B perp squared is crucial, just what you said. And that generates the K perp squared dependence of the TMDs and so on. But then as I emphasized before, just to say it again, you never see K perp squared alone. It always comes with an x1 minus x downstairs, because that's the invariant mass formula. We heard that from your lecture. Okay. Is it still there somewhere? I don't know. Way up at the top. All right. So people have been playing with this and so on. They actually they take these models. Here these guys do the Wigner distribution, but they also did, it's hard to read, isn't it? It's terrible. They get the different C-quark distributions and so on. You know, people are playing with this and so on. There's a large literature on just simply people starting with the ADS wave functions, and then you, at the scale Q0, you apply which is the factorization scale, you then apply deglap evolution. And here's another one that I was involved with. This is the strange quark distribution and so on. You can read the details with Determan, Liu, Sofian, and so on. And there's really a lot you can do here. And you see, in fact, that the S quark and the S bar quark are not the same. This is now evolution, but it also has in it the physics that the S and S bar are connected back to the proton. The proton is UUD, so the S and S bar are not the same. And as I mentioned in my first lecture, you should never expected S and S bar to be the same, because in the non-perturbed domain, they're conjugate to the lambda kaon, and the kaon couldn't be more asymmetric between the S and the S bar. So you get this, you can do the spin dependence and so on. So you get actually new predictions for the S and S bar. Oh, please, yes, go ahead. I'm sorry, I can't hear.
Maybe you mentioned that, when you extract the PDX from the light from,
Yes.
where does the Q square dependence?
Oh, yeah, so what you do is you pretend that Q0 is the factorization scale. And then and then you start as an input with the quark distributions. Then you start applying deglap evolution, which generates the gluons, which generates the C quarks, and so on. But now it's now you have to do, if you're careful, you include the interactions back to the valence quarks.
So you don't get deglap from here.
It's a modified deglap. If you go to very high scales, it's the simplest deglap, because then the system forgets everything. Actually, you remind me, though, of something which I wanted to say. In this potential, which is cap of the fourth zeta squared, which is cap of the fourth B perp squared x1 minus x for, say, a two-particle system, the potential vanishes at x equals 0. So that means, in fact, that if you look at the pion and then look at a light quark, a C quark, far away, very low x, it's far away in rapidity, it's not confined to a guy with high x. You know, that's something it always bothers people. How is it that deglap evolution, which keeps producing particles which are further and further in longitudinal space, how can they stay confined? Well, it turns out the confinement potential is there, but it's weaker and weaker. Isn't that amazing? I mean, I never knew that. I never thought that, in fact, you could actually have large longitudinal separation in a hadron, but you do. This potential actually weakens as x goes to 0. So that's a new game in town, because it's mind-blowing in some ways that you can actually do this. And I know people have written papers on this and said, how can it be that the valence quarks are here and the C quarks are way out there? If you just translate that to distance, it's huge distances. Well, the potential actually is flexible. It's amazing. All right. So now I wanted to go back to this, which is work I did with Marcus Deal and Daiseng Wang. And also, Marcus has done similar work with Feldman and Jacob and Peter Kroll. And the idea is, how do you compute all the deeply virtual Compton scattering amplitudes, which people love? And the answer is, you do it. It's the Drell-Yan-West formula with the same type of idea. You have overlap of light front wave functions. That's what these are. However, you have to, if you're honest, you have to include not just the quark going in and the quark going out, you get actually herbal contributions. That's the contributions where two quarks can come from the same guy. Anyway, I don't want to go through the whole story, but there's a huge amount of algebra that goes on to do this. And then you can start with this amplitude here, and you can look in different regions, and you get, in fact, contributions from this, and so on. So it's really, there's finite formulas. So here's a little bit more of this. Is you start with the protons, say. You take a quark out. This is the usual handbag diagram. This gives you the usual cut, which gives you the Bjarkane x is equal to the light front fraction of the x of the quark that you struck. So that's this. But now if you're doing Compton scattering, you have a cross graph. So that's in there. Then you also have graphs, though, like this, because now, unlike what we had in the Drell-Yan-West formula, because you have a photon in and a photon out, you have to have non-zero plus momentum coming in or out. And so now what happens is that you actually can get graphs like this, where the plus momentum, this guy has 0 plus momentum. You can choose a frame like that. But you've got to choose one where this guy has finite plus momentum. And so that means you can drag out Fock states with an extra QQ bar. And unless you do that, you don't get the gauge invariant answer. And then you get the cross graph version of this. So we computed all these just to see that it works, and we made little model calculations. All right. And this is long ago. Coleman and Norton analyzed these graphs, but you have to, in fact, include all these diagrams to get it right. So then you can look in general, you can look also at this problem. So here's the GPDs, and you have the handbag diagram, so that looks simple. I've now just simplified the analysis down to the handbag diagram, but now you have gluons which go across in the intermediate state. That's what produces, number one, the Sivers effect, which we talked about last time, which is this which comes from the final state interactions, because if you cut this diagram in deep elastic scattering, it's the gluon scattering between the struck quark and the spectator quarks. It happens again and again. So you have to put in all the gluon interactions on that handbag diagram. So this is terrible, but you have to do it. And this leads to lensing effects is sort of one way to surprise it. In QED, it's the Coulomb phase. But because you have, the proton has both S wave and P wave, you get two different Coulomb phases, you have to be careful. And then not only that, these gluons are soft gluons. These gluons, their scale is not Q squared. Even in QED, you can look at that. They're soft photons. So this is another problem. Another virtuality comes in, the virtuality of those exchange guys. So what I'm doing is I'm not saying I've solved this problem. I'm just saying, or learning you, that the data has this in it. And this leads not just to the Sivers effect, but diffractive deep inelastic scattering. Diffractive deep inelastic scattering is the case where you can produce the photon can produce, say, a row-like meson, but its whole excited QQ bar system, two gluon exchange in the T channel, and that leaves the proton intact. You get color singlet separation. And that's leading twist. And it comes from, again, gluon interactions. So I think next time I'll show that briefly. I don't think I have it in this slide. So now people have computed the H and the E distributions and so on using these initial amplitudes as a starting point, but ignoring this problem with the gluonic corrections. Now here's something I did with Adam Szczepaniak. He's not here. Yes, he's here. Okay, so this is something we did with Linus Estrada, and it's also related to earlier work I did with Frank Close and Jack Gunyon. And the point is the following, is that you guys heard a lot about this instantaneous Fermat interaction, right? So this is a local interaction. It's actually 1 over K plus is the denominator, 1 over K plus. However, it's exactly the same answer you get if you had squarks in the proton. So let me remind you, if you had scalar charged particles, you always have two photons interacting locally on the quark, on the squark in that case. So the analog of that is this guy. It's the Siegel interaction come to life. Now, why is this interesting? Because it's phenomenologically important. It produces a real amplitude which actually is energy independent and independent of the virtuality of this photon even. All sorts of interesting facts about it. Now, you could say, well, I don't believe in this graph. If you use Feynman rules, it's there. So when you do the numerator algebra in Feynman, you have the k slash plus m upstairs. There's a k minus gamma plus in the k slash. So you write out k slash. Then there's a k minus gamma plus. That k minus wipes out the denominator, leaving behind this 1 over k plus. So it's there in the Feynman rules. We just don't recognize it. We keep thinking that this diagram doesn't exist. It's actually the k minus wipes out the denominator. And that's why you get this local seagull-like interaction. So that's right. So here it is again. The scattering amplitude is a quark squared divided by x and the epsilon vectors like this. And then, so 1 over x because of the 1 over k plus. So that's unusual. It's not the structure function with x in the numerator, it's x in the denominator. That's interesting. But also the amplitude is just like the seagull operator, it's actually s to the 0. In Rangi language, it's an amplitude which is energy independent, unlike any other hadronic amplitude you've ever seen. Hadronic amplitudes in Rangi language goes typically like the square root of s. This goes like s to the 0. But also that square root of s depends on t. When you do Reggie theory, you guys are too young, you actually predict that the amplitude goes like the square root of s, and however that's at t equals 0. At larger t, that Reggie pole recedes to actually negative values. This guy is there forever. The power is always 0 because it's a local interaction. It happens because we have local photons. You would never see this in hadron-hadron scattering. You don't get this. However, for 2 photons, you see it. So this is also what people relate is called the D term in deeply virtual Compton scattering, which plays a major role in deeply virtual Compton scattering. And it's also when people analyze the muonic hydrogen Lamb shift, you have to put in the dVCS amplitude, and you have to calculate that. And this term actually, I don't think people have done a good enough job on it, but this is the basic graph that's not understood well. So we need much more measurements of this thing. In fact, all people have to do is look at d sigma dt and isolate this s to the 0 amplitude, which is energy independent. And it's a light front instantaneous interaction in the front form. In the Feynman rules, it's just this idea of k minus gamma plus in the numerator. But it's analytic. So here it is again. And also, if you go to large angles, the amplitude, first of all, the region is at j equals 0. It's called a j equals 0 fixed pole. The form factor associated with this is like a proton form factor. It's a new form factor. And it goes like 1 over t squared. And then, in fact, the cross-section, if you do large t and large u and large s, it goes like 1 over s squared, because the amplitude is s to the 0, 1 over t to the 4th. And then it's 1 over s to the 6th at fixed t over s, which is fixed center mass angle, which is exactly what you get for dimensional counting rules. So people see that. That's been observed, the 1 over s to the 6th. You see 1 over s to the 7th for pion photoproduction, kn photoproduction. However, the Compton's 1 over s to the 6th. But what's really got to be done is a careful analysis to pick out this piece, because it's the piece that's crucial for the dispersion theory, for example, deeply virtual Compton scattering. Okay. So here it is again. It's also the 1 over x is interesting because it's in the Feynman-Hellman theorem, you're taking m squared over x for the expectation value of the mass of the quarks. So this coefficient that appears in here, 1 over x, is the one that appears in how you calculate the mass squared of any parton. It's also its contribution to the hadron mass. So it's a fundamental test of local gauge theory, and it has also this feature as well, that because the 1 over s squared cancels, you only get, from this graph, you only get this guy. So here I drew it as a seagull, but it's actually the instantaneous fermion line. Oh, here it is in Reggie language. I forgot I had this. Alpha var. Normally you see, in fact, regions that go up and up and up. This one actually is a region which goes to, at t goes minus infinity, goes this way. In fact, that's what you would see in the data because all the other regions recede, and so you just, in fact, will see this contribution at t equals 0. So this, it says, in fact, that you get, well, this is actually now for the case of, oh, I'm screwing this up. Yeah. That's for 2 photons. There's also, you can do this for gamma proton goes to pi proton. I'll skip that. But here it is, gamma star gamma p. It goes like this behavior right here. All right. Okay. So we typically use a handbag approximation without worrying about it. However, it assumes that the current correlator is carried by a single quark propagator. It's the imaginary part of the forward amplitude gives the structure functions. That's true. However, as soon as you get to photons of different virtuality, now you have the diagrams where you go from 5 quarks, 4 quarks, quark antiquark to 1 quark and so on. Then you have all the diagrams with the gluon exchange and so on. And there's also problems when you get to nuclei, which I will show you in fact. But remember, the Sivers effect is built in, and you have to include then all the gluon interactions in there. Okay. All right. Well, let me now interrupt this discussion and go to something else. How much time? I have enough time. 15 more minutes? Huh? How many? I'm sorry. 5 minutes. Okay. All right. So I want to show you a little bit about we'll continue next time with some of these phenomenological things. But here I wanted to show you something interesting. That is, suppose you start with the Higgs theory, the standard model that won the Nobel Prize and so on. Same Lagrangian, but now you use light front. You don't use ordinary quantization. Everything comes out the same, but better, right? It's the same theory. And the Higgs field itself is interesting. The real part creates the Higgs particle, 129 GeV. The imaginary part becomes the longitudinal components of the W and Z. That's exactly what you see in standard analysis. However, the VEV, which is the Higgs, which is sitting in this Higgs potential, is not oscillating. It's not a 1/2 h bar omega thing. It's just a constant scalar field. And I think about it like a Stark field in the background of atomic physics, a constant background. It's different in the front form. You don't have the 1/2 h bar omega. It's rather amusing. So that's what this is. And then, in fact, because it doesn't have any momentum or energy, it doesn't appear in the trace anomaly. That's pretty interesting. So that means gravitons don't see it. See, normally what people say is, well, the Higgs is outside everywhere in the vacuum, and therefore it's oscillating, so you get 10 to the 54 from the vacuum. Not true here. So here's a paper I wrote with Prem Suristava, which actually goes through everything very carefully. We also showed how to by the way, in another paper, how we quantize the theory in Feynman gauge, because you were interested in that, I think. So that's another paper. But this is now doing the complete front form analysis of the standard model and verifying basically everything. But as an exercise, we just give this example where you have spontaneous symmetry breaking. So you just construct a theory which has got a scalar potential, and it has a expectation value and so on. But it turns out that the answer is just v over square root of 2 in this model. It's just a square, it's just a constant background field. So the Higgs is not an oscillating field that oscillates everywhere in the universe. It's just simply a constant background field. Okay. Now, what I've talked about is actually flat field gravity. Nobody's analyzed this problem in a curved universe. Maybe, in fact, you get some contribution to the cosmological constant, for example, in a curved universe. I don't know for sure. But at least this thing, it eliminates the famous 10 to the 54 problem for the Higgs theory. Now, this is what Craig talked about a little bit, that if you look at the conservation law for the axial current, you should get the gamma 5 contribution. Well, this is true, but you need a matrix element of this guy. This side is just the usual thing that gives you the decay constant, But here, you get this extra contribution from the quark masses. So everything comes out right if you do this thing. So that's fine. And so current algebra, what people usually say is vacuum to vacuum. It's not vacuum to vacuum. You just have vacuum to pion is all you analyze. And the vacuum to pion connects this guy to this guy. So there's really never a place where you have vacuum to vacuum in the Gelman-Low analysis. And that's been very confusing to people because they just sort of did this for convenience, wrote vacuum, but they should have kept the pion field there. And then you get, in fact, matrix elements which connect this guy to this guy. All right. So let's see. So I mentioned this already, and so I'm going to go back. All right. So you get now the whole Glashow-Weinberg-Salam theory correctly. You get the non-abelian Higgs theory, and you can use, this should be light cone gauge. It's a mistake. Unitary renormalizable. The perturbative vacuum, there's really nothing there, but you get the zero mode field. All the 't Hooft connections are there. Higgs field creates the Higgs particle. The imaginary parts just do the normal things, W and Z, but the Higgs VEV is replaced by a zero mode. So you get the same phenomenological consequences. The Higgs field is 3 components. The Higgs VEV of the instant form, which is this oscillating thing, which everybody imagines gives this gigantic contribution to the cosmological constant, is not there. Okay. So here's what Tony Z wrote. He says, actually 10 to the 56, I said 10 to the 54 by mistake. He says the electroweak theory gives 10 to the 56. Not true. He says QCD gives 10 to the 45. The real answer is 0.76 if you accept phenomenology. Well, in the front form, you get 0 and 0. So that's the answer. Okay, I will stop there. Yeah, sure. Okay.